The air is thinner here. Every breath delivers less than it should. Your lungs pull hard and still come up empty. Your head pounds. Your vision narrows at the edges. You've only been climbing for a few hours, but your body is already sending signals that were never meant to be ignored. Most people, if dropped here without preparation, would collapse within days. Your organs would begin to fail. Your brain would swell. Your lungs would fill with fluid. The mountain does not negotiate. And yet, for roughly 15,000 years, human beings chose to live here anyway. Not to visit, not to pass through, to build homes, raise families, hunt, sleep, and die in some of the most oxygen-deprived terrain on Earth. High above the clouds, on plateaus and peaks where the atmosphere itself becomes your enemy, ancient humans survived. And in surviving, they changed. How did they do it? The answer involves some of the most remarkable biology in the entire history of your species, and a group of ancient humans who were not quite like you at all. Let's start with what altitude actually does to your body. At sea level, about 21% of the air around you is oxygen. That percentage stays almost constant as you climb. What changes is pressure. At 4,000 meters above sea level, roughly 13,000 feet, barometric pressure drops so significantly that each breath you take delivers only about 60% of the oxygen it would at sea level. Your body detects this immediately. Your heart rate spikes. Your breathing becomes rapid and shallow. Your blood thickens as your body desperately tries to carry more oxygen per cell. This emergency response has a name: acute mountain sickness, AMS. Your body is doing exactly what it evolved to do at lower altitudes. It is getting it badly wrong for this new environment. In severe cases, fluid leaks into your brain. That is high-altitude cerebral edema, or HACE. Fluid leaks into your lungs. That is high-altitude pulmonary edema, or HAPE. Think of those as the mountain's two final warnings. Both can kill you in hours if you do not descend. Your ancient ancestors knew nothing about cerebral edema or pulmonary pressure, but they understood the high places were dangerous in the oldest possible way. They felt it in their chests. They watched companions grow weak and confused. They saw what the mountain took from people who were not ready. And some of them climbed anyway. Archaeologist Kurt Rademacher and his colleagues made a discovery in 2014 that forced a serious reassessment of what early humans were capable of. At a rock shelter called Cumcaicha in the southern Peruvian Andes, they found stone tools, animal bones, and hearth remnants dating back approximately 12,400 years. Cumcaicha sits at 4,480 meters above sea level. That is nearly 14,700 feet. Not a temporary camp near the base of a mountain, a high-altitude settlement, deep in the Andes, occupied by people who had been on this continent for only a few thousand years and had already figured out how to survive where almost nothing else did. What were they doing up there? Hunting. Specifically, they were hunting the vicuña, a wild relative of the llama, with wool so fine it has no equal in the natural world. The vicuña lived at altitude precisely because its predators mostly did not. Early Andean hunters followed them up, and some of them never came back down. But surviving up there required something deeper than strategy. It required the body itself to change. This is where the biology becomes extraordinary. Anthropologist Cynthia Bell spent decades studying high-altitude populations across 3 continents and identified something that shifted how scientists understand human evolution entirely. Tibetans, Andeans, and Ethiopians all live at high altitude. All 3 groups face exactly the same oxygen problem. but they have each solved it in a completely different way. Andean highlanders, the descendants of those earliest Kunkaicha hunters, produce significantly more red blood cells than sea-level humans. More red blood cells means more hemoglobin, the protein that ferries oxygen through your blood, which means more oxygen delivery even when the air is thin. It works, but it comes with a cost. Blood this thick is harder to pump. Hearts enlarge under the strain. Over generations, a condition called chronic mountain sickness can develop. The body pays interest on this adaptation for the rest of its life. Tibetans solve the same problem differently. They do not produce extra red blood cells. Instead, they process oxygen more efficiently at the cellular level. Their blood carries unusually high concentrations of nitric oxide, a molecule that keeps blood vessels wide and flowing freely despite the altitude. They breathe faster than Andeans, but their organs are shielded in a fundamentally different way. Less metabolic debt. Ethiopian highlanders, particularly the Amhara people, are perhaps the strangest case of all. They show almost none of the typical physiological changes. Their hemoglobin levels look close to sea-level normals. How they function at high altitude without any of the visible adaptations their Tibetan and Andean counterparts carry remains, in Beale's own framing, one of the most intriguing open questions in human biology. 3 populations, 3 mountains, 3 completely different evolutionary answers to the same problem. The Tibetan solution, it turned out, had a stranger origin than anyone anticipated. In 2014, geneticist Rasmus Nielsen and colleagues published a paper tracing the source of Tibetan's most powerful altitude adaptation back to an ancient human group called the Denisovans. The gene in question is called EPAS1. It regulates how your body responds to low oxygen. Tibetans carry a version of this gene that is extraordinarily rare in any other living human population. The only other group ever found to carry it, Denisovans, a separate branch of ancient humanity, neither modern human nor Neanderthal, who vanished from the earth tens of thousands of years ago. At some point in the deep past, modern humans moving into High Asia interbred with Denisovans. Most of what passed between our species dissolved into the broader gene pool without a trace. But the EPAS1 variant that the Denisovans carried gave such a powerful survival advantage at altitude that natural selection locked it into Tibetan populations and held it there. It was too useful to lose. Your ancestors were rescued from the mountain by the genes of a species that no longer exists. Now, let's reconstruct what a day at 4,000 meters actually looked like, roughly 10,000 years ago. You wake before sunrise in a shallow cave or a skin-draped shelter pressed into the cliff face to block the wind. The cold here is not the negotiable cold of lower ground. It cuts through material and does not apologize. Your fire went low in the night. Reviving it is the first task of every morning, and it demands tinder that is scarce at this elevation, where trees do not grow and firewood must be carried up by hand or traded for at great cost. Your morning meal, if there is one, is dense. At altitude, your appetite suppresses. This is one of your body's least helpful responses. You need significantly more calories to generate heat and power a cardiovascular system working harder than it should. But your stomach sends signals of fullness even when it's nearly empty. Ancient highlanders learned to eat fat, marrow, and dried meat in concentrated form because eating for volume at altitude is a trap your body sets for itself. The hunt begins when the light is good enough to see across the plateau. You move in a group, not only because tracking bigunyas requires coordination, but because the cold and the thin air demand it. A hunter who pushed too hard and collapsed alone was a hunter who might not be found until spring. Movement at altitude is a constant negotiation. You can't sprint, you can't sustain the kind of exertion that felt natural at lower ground. The hunters who endured were not the strongest. They were the ones who learned to read their own bodies and never spend energy they didn't have.
Children born at altitude absorbed these lessons before they could speak. Their lungs developed differently in the womb and in early childhood. Their hearts. By adolescence, their capacity to extract oxygen from thin air was measurably greater than any sea-level human who trained for years trying to replicate it. The mountain built them from the inside. Mark Aldendorfer, one of the leading archaeologists of the Tibetan Plateau, has documented evidence of human presence at high altitude reaching back tens of thousands of years. The plateau was not conquered in a single moment. It was negotiated, season by season, generation by generation, by bodies slowly becoming something new. Not all who tried survived. Not all who survived stayed. But enough did, and the ones who stayed changed the genetic
inheritance of every person who descended from them. Here is the part that changes the whole story. We tend to think of high-altitude survival as an endurance narrative, people suffering through a hostile environment because they had no choice. But the evidence from Kunkaicha, from the Tibetan Plateau, from the Ethiopian highlands tells a different story. Early humans chose the high places, deliberately. The peaks offered things the lowlands did not: fewer predators, resources that competitors below could not reach, sacred geography, because mountains held spiritual significance in nearly every ancient culture that lived in their shadow. Trade routes through high passes that connected distant peoples separated by impossible terrain. The high places were not exile, they were strategy. The body followed the choice. Evolution, as it always does, caught up with what humans had already decided. You breathe a little harder than you need to at sea level, but somewhere in your genome, coiled across billions of base pairs, is a record of every altitude your ancestors dared to climb. The Denisovan contribution, the EPAS-1 variant, the thick blood of the Andes and the efficient vessels of the plateau, and the quiet mystery of the Ethiopian highlands. The air is thinner up there. Every breath delivers less than it should. Your ancestors knew that. They climbed anyway. And the mountain, in the end, had to make room for them.